Welcome to the Institute's seminar. So it's a pleasure to be introducing the speaker for today, Professor Sirish Shah. So Professor Sirish L. Shah has been with University of Alberta since 1978, where he held the NSERC, Metricon, Suncor, ICOR Senior Industrial Research Chair in Computer Process Control from 2000 to 2012. He is a recipient of several awards. Some of them are Albright and Wilson America's Award of Canadian Society for Chemical Engineering, Killam Professor in 2003, D.G. Fisher Award of CSCHE for significant contributions in field of systems and controls, Aztec Award in 2011, IEEE Transition to Practice Award in 2015, 2017 RSJN Award of the CSCHE, etc. He has held appointments at various places, visiting appointments at such as Oxford University and Balliol College, Kumamoto University in Japan, University of Newcastle in Australia, IIT Madras, National University of Singapore. He is an authority in several areas of AI and machine learning and their practical applications in the process industry, including data-driven approaches to anomaly detection, alarm management, fault diagnosis, model identification, optimal and safe plant operations, process control, controller performance benchmarking, etc. He has co-authored several books, in particular three books he has co-authored, titled, one of them is on performance assessment, one is on process nonlinearities and wall stiction using data-driven approaches, and a recent monograph on capturing connectivity and causality in complex industrial processes. He is Emeritus Professor at University of Alberta, Fellow of Canadian Academy of Engineering and the Chemical Institute of Canada and the IEEE. Another of his noteworthy contribution, which is really important for, let's say, our country, is that he has made seminal contributions to the development of control, especially process control community in India. A large number of academic researchers and several industrial practitioners in this area in our country have either worked with him as students or have been mentored by him. So currently he is Rajesh and Nisha Chair Professor at IIT Bombay, which has facilitated his visit to IIT Bombay. So over to you, Professor Sirish. Thank you.
Okay. So thank you, Mani, for the kind introduction. It's always a pleasure to come to IIT Bombay. So before I begin, I want to acknowledge the donation from Nisha and Rajesh Raman for the endowed professorship at IIT Bombay. And also thank the director Professor Subhasis Chaudhary for appointing me in this role as a visiting professor. As I mentioned, it's always a great pleasure to come to IIT Bombay, and I want to acknowledge the many years of interaction that we've had between IIT Bombay and the University of Alberta, and I want to name people who really gone back and forth. We started off with Ravindra Goody. He was a PhD scholar at the University of Alberta. Thereafter, we had Sachin Patwardhan, Kanan Mudgalia, Mani Bhushan, all of them having spent more than a year or longer at the University of Alberta. And in addition to this, we've had many postdoctoral fellows and other students come from here to the University of Alberta. And also the reverse, we've had quite a few of the University of Alberta professors coming to IIT Bombay. Case in point, most recently, Professor Nanda Kumar was here. Jacob Maslia, I hear, was here a few years ago, Murray Gray, and others from Alberta who have had the pleasure of visiting IIT Bombay. Okay, so now to start on my talk, I'm going to explain the title shortly, but I just want to say that this is more of a perspective talk, with a very simplistic overview of artificial intelligence and machine learning. I'm not going to go into the details. I think the main the main purpose of this talk is to show the role that AI and machine learning can play in the application, in the challenging applications that are likely to be of great societal benefits. And I'm going to share some of those challenges with you. No real answers, but something to think about. So let me start by defining the term analytics. This is the term that I will use time and again. And if I want to define the term, here is a very simple definition. Analytics is the discovery and purposeful utilization and communication of meaningful information and patterns in your data. What you want to understand from this is you want to turn data into actionable information. Not just turn data into more data, but something that's tangible, that makes sense. And what has propelled the widespread interest from academia and industry into analytics and AI and machine learning is the availability of massive volumes of data. Massive volumes of data, powerful algorithms, and of course, fast computers. So there is widely growing interest from academia, governments, institutions everywhere in this area, and a lot because of quotes such as the following. And so I quote, "Information is the oil for the 21st century, and analytics is the combustion engine." So this comes from Gartner Research. Gartner Research is a very reputable industry advisory and consulting firm in the US. Another interesting quote comes from Andrew Ng, who is the director of AI at the Stanford University lab, and he has said the following, quote, "AI is the new electricity," end of quote. A powerful statement, and you can relate this to the discovery of electricity, which has allowed inexhaustible application. Most of you have grown up with electricity. People who are senior like me, who go into villages where there was no electricity, you walk around with lanterns and so on. That's when you realize what electricity has done to our lives. So, and he goes on to say that AI might be the single largest technology revolution of our times. And we are already living in an AI-led era. Talk about Alexa from Amazon or Siri from Apple or the Google Assistant. You know, these are powerful assistants. All our smartphones are equipped with personal assistant powered by AI technology, and they are more than 90% reliable and dependable. So what is propelling the need, the drive to AI and machine learning is the massive volumes of data. And this brings me to this second quote here. It comes from Eric Schmidt, at the past executive chair at Google. And he goes on to say, there were 5 exabytes of information created between the dawn of civilization up to 2003. 1 exabyte is 1 billion gigabytes. Just think. Okay? And goes on to say, but that much information is now created every 2 days. I don't know how they get these numbers from. A lot of this is video and graphics information and so on. Nevertheless, massive volumes of data. All right, so looking ahead, fast networks, computers, and algorithms is certainly propelling a drive for better productivity and performance. So the world is changing at an unprecedented speed. And certainly, AI, machine learning, deep learning methods are making it possible to have intelligent conversation with platforms such as ChatGPT. Now realize that not everything is accurate that you get from ChatGPT. It's having problems counting numbers, sometimes doing simple algebra and so on. Nevertheless, it is helping us in the accelerating drug discoveries with molecular simulations, plus many other widespread applications. And I'm going to talk about some of these types of applications. So easy access to AI and machine learning means that powerful algorithms will be available easily, and this will lead to the democratization of information for everyone. Think of people from Algeria to Zanzibar. Everybody will have their access to incredible resources at their fingertips. So that's what they mean by democratization of information. And this will allow everyone to explore and be creative and look at ideas. Okay? So of course, this will allow us to also work at challenges such as the following. Many of you, the next generation of engineers, will have to work with challenges to deal with food, water, and energy security. We want to ensure, with a growing world population, we want to ensure that there is food, energy, and water security for everyone. There will be, we will need to improve efficiency and productivity, keeping in mind the sustainability, the environmental, social governance, and such issues in mind. Sustainability is becoming an important point in government and industry as well. And there will be short-term as well as long-term societal benefits. In healthcare, for example, and I give you an example. It was just very recently in 2020 that MIT professors Brasile and Collins announced the discovery through deep learning of a new drug called halicin. This is the first antibiotics that has now been discovered after 30 years. We've not had any new antibiotic discovered for since 2020, before that for 30 years. Okay. So the researchers use AI to search through millions of candidate chemical compounds. And by first training them on chemical structures of known antibiotics and how well or how poorly these antibiotics were able to deal with specific types of bacteria. And then the AI algorithms spat out a short list of potential candidates. So it will still take many more years for these drugs to go from the lab to clinical trials and final products. But nevertheless, AI has accelerated the search for discoveries of new drugs in this way. And this same idea can be applied for material discoveries, for new materials, for batteries, and so on and so forth, for new catalysts, for example. And the increasing use of sensors everywhere through the Internet of Things here has also allowed us to improve productivity and use this data very productively. AI, of course, with better monitoring will allow process systems to work with improved safety as well. All right, so here is the outline of my talk. I'm just going to give you a very simplistic overview, but I'm going to spend most of the time in discussing three very broad applications. And the terms that I have used in my title, reimagining system science. So the point I want to make is we now have to think of how to apply some of these new tools available in AI and machine learning, how to apply them to deal with a very broad and challenging number of applications, and look at this from a system science point of view, look at the problems holistically. And I'll give you an example as we go through. For example, for battery development, you have to look at the entire life cycle of a battery, from mining resources right up to the time the batteries have to be recycled and so on. And how do you put it all together? Okay. And lastly, I will finish up with a very simple example to show that the application, you don't need rocket science to come up with very simple machine learning applications that are of great use in industry. And I will continue to also highlight this point about data ingestion. You need to really take data into account, and you need to work with good data at all the times. And this is the most difficult part of most AI and machine learning application. All right, so let's talk a little bit about transformer models. Generative pre-trained transformers, commonly known as GPT. These are a family of neural network models that uses the transformer architecture that is the key advancement in powering generative AI and in products such as ChatGPT. In 2017, Google authors published a paper, and the title of the paper was, quote, "Attention is all you need," end of quote. Okay. And this was a key paper which allowed the development of large language models and so on. So let me explain this. So this paper led to the transformer model that learns context in a sentence, context and therefore the meaning by tracking relationships in sequential data. So it gives numbers to unique words in a sentence, and it also tracks the location of these words in a sentence. And you could have a whole sequence of sentences, and it's able to then relate the meaning of a sentence. So let me give you an example. Here is one sentence. The pizza was baked in the oven, comma, it tasted very good. English is a difficult language. So the question is, what tasted good? The oven or the pizza? So I repeat, the pizza was baked in the oven. It tasted very good. In the context, we know that it was the pizza, but when you are asking the machine to interpret a language, a sentence like this, or a whole string of sentences, the paper attention and self-attention was able to track the existence of these words throughout this string of sentences. And this is the power that this paper has generated, which created platforms such as ChatGPT and generative AI. Okay, so transformer models apply an evolving set of mathematical techniques called attention or self-attention to detect subtle waves, even on distant data elements in a series, so large sentences or a sequence of sentences, and detect how they influence and depend on each other. These ideas can be applied not only to text data, but also to images, speech, and so on. You can use all of this now to train foundation models, which can then be used to deal with tasks such as information attraction, chatbots, for example, answering questions, image captioning, and so on, object recognition, and so on and so forth. Okay. So the other challenge that I want to also communicate to you is the following. And for this, I look for an image that serves as a metaphor for the torrent of data that comes to us. You know, no matter what you're doing, you can have so much data coming to you. So data comes in many shapes and sizes, meaning many different formats, many types of data. And here is an example. You can have spectroscopic data. It can be spectral data. It could be time series data. You can get data in 3 dimensions. For example, if you're dealing with an agro-hydrological system that I'm going to be talking about, you know, in 3 dimensions in space and time and depth, for example, or if you're mining, you know, you're looking for seismic wave data and so on. You can have pixelated cluster of statistical data. These are not musical notes. This is perhaps vibration data from a rotating machinery, commonly used to detect abnormalities in rotating in other machineries. You can get image data. You can also work with process connectivity data. How are processes or industrial organizations connected to each other? The supply chain for information, for example. You can look at business data, and now, of course, you have natural language processing and large language models and so on. So the main point here is, unless you are armed with the right flotation aids, and think of flotation aid as unless you're armed with the right analytic tools, you can easily sink in the sea of data. You need to have the right set of tools, and it's a challenge to work with many different types of data and put it all together. All right, so what is AI? AI is software or algorithms that can reason, infer, and think like humans, and sorry, I didn't turn the clock on. I have to. Okay. So AI is algorithm software that can reason, infer, and think like humans, or it is the practice of getting machines to mimic human intelligence and perform tasks that humans can do. And it's comprised of many different areas. We're mainly going to focus on machine learning, but I just want to point out here that knowledge and inferencing is important for developing soft sensors. I will talk a little bit about this. And then learning probability is important in the insurance and risk area. When you're dealing with safety issues in a plant, you want to be able to do risk analysis. And of course, now there is a lot of interest in NLP, natural language processing, and so on, which platforms such as ChatGPT and them are using. We're trying to build large language models for specific applications and so on. So interest in AI from industry and government and academia is very high because also of the availability of large amount of information. And I show you this graph here just to drive home a point. The explosion of data, the Internet of Things, connected devices, the installed base worldwide from 2015 to 2025. Just look here. There has been a 5-fold increase in IoT devices. 15.4 billion devices here, more than 75 billion devices here. Just over 10 years. And this is exploding like anything. Okay. Now, talk about data. We talked about exabytes, but look at this article appeared in 2019 issue of IEEE Spectrum. Question was data floods, how much to store and for how long, and they're talking about iota. Here is exabytes, 1 billion gigabytes. Iota is 1000 to the power 8, so 10 to the power 24, and they're already talking of iota, which is 10 to the power 48 bytes of information. Where to store and how much to store is the question. All right. ChatGPT and large language models, the objective in AI-based technology is to emulate and model human intelligence. Not easy to do. Human intelligence is complex. As we pointed out earlier, it is highly contextual. All right? Not easy to capture domain expertise and put it together with the information that you get, because oftentimes domain expertise is tacit, it's hidden, it's implicit. When I gave this sentence, the pizza is baked in the oven, it tasted very good. We know pizza is something that we eat. We don't eat ovens, so there is a lot of implicit information in the way we communicate. So not easy to capture and especially not easy to automate. AI systems based on large language models need training on massive volumes of data. GPT-3 was trained on 45 terabytes of text data. That's about 1 million feet of bookshelf space, or a quarter of the entire Library of Congress. And this came at an estimated cost of several $1 million. And the other important thing to know is that ChatGPT required many months to train, many more months for the models to be validated and monitored. So the LLM models are based on multi-layered neural network models that have trillions of parameters that they have to work with. And the other important thing to remember is that generative pre-trained transformer, GPT, these are a family of neural network models. And essentially, these LLMs are black boxes, systems which do not fully understand the relationship between input, training data, and output. The result is that the response from ChatGPT is often plagiaristic. It will quote you something from another source and it will not give credit to where it's gotten this information from. Okay. So meaning it reproduces large chunks of text information from other sources. Okay, let's look at this. So here is the timeline. This may be difficult to see, but all I want to say is that ChatGPT was introduced in November of 2022, barely 15 months ago. Already in the first 2 months, it gained a record 100 million users in 2 months. 100 million users in just 2 months, and generated a huge amount of interest. Since then, many other software, so there is some animation here, since there are many other software vendors have entered the market, and they have some very niche products. For example, here, Bloomberg announces an LLM trained on financial data and so on. So people are looking at some very niche markets now. Okay, so just something to be aware of historically. The whole idea started with deep learning. Deep learning is this multi-layered neural network model. The work that was done by Jeff Hinton in the middle at the University of Toronto, Yoshua Bengio at École Polytechnique in Montreal, and this is Yann LeCun, who is now at Meta or Facebook. There's Canadian Institute for Advanced Research, CFAR Fellows. They received the AM Turing Award in 2017 for their work on deep learning. And this is the framework that is being used for all of these models. This is often referred to as the Nobel Prize for Computing. Both Hinton and Bengio have discussed and commented widely on the potential promise of AI, but also the perils of AI. They have said very openly that AI will certainly help in discovering wonder drugs, accelerate the discovery of advanced materials for many purposes, but it can also be used to spread misinformation, it can be used to spread propaganda, and it can give you direction to build a destructive weapon. So we have to be mindful how AI is used. And therefore, governments and institutions, including academic institutions, have to now have the rules and legislative machinery to put checks and balances on how AI is being used. All right. So something that just came up recently in the Economist, Frank Rundat, a software engineer, said the following: one day we are going to look back and wonder how a company such as OpenAI had the audacity to copy all the world's information and enable people to violate the copyright of these works. And the case in point is, somebody asked ChatGPT to write an article on a specific subject. What popped out from ChatGPT is an entire verbatim article from the New York Times. No copyright was expressed. No copyright infringement was expressed. So now there is a lawsuit from the New York Times to OpenAI and so on, and this is going on. And same thing applies to OpenAI scanned and hosts all the content in, and it sells access to it and will even generate derivative works for their paying users. So there is lots of plagiarism that's going on, and generative AI will in fact propagate this even more. So you want to be mindful. So whenever you're using, I'm sure many of you are using ChatGPT, but you have to ask the question and look and put in your critical judgment here, okay? Midjourney as well is selling images that it may have captured from somewhere. No copyright terms are given. All right. So very simply, we're going to be looking at machine learning, and in a very, as I said, very simplistic viewpoint. We are not going to talk about reinforcement learning or self-supervised learning. Those are newer terms. But unsupervised learning means find hidden patterns in your data. The data is unlabeled. We don't know what the cause and effect variables are. All we have is a big box of data and analyze it. And this is unsupervised learning. If you know, if the data comes to you labeled, there are cause and effect variables, input and output variables, we can do what's known as supervised learning, all right? The most important thing is no matter which type of learning, the informative data, good data is the most important thing. You need good data to make your models work. You may have heard the term, the data, garbage in and you get garbage out. So important thing is to be mindful on what type of data are we using. The other important thing here is there are many methods which will allow you to do unsupervised learning. It's mainly to cluster your data, sort it into groups. And even if you have labeled data, it's always useful to do some type of clustering analysis. When you have labeled data, you can do supervised learning to build regression models or to do classification. Okay, and there are many techniques. And the reason this is not an exhaustive list, I just point this out, came from MetWorks. Here under regression, you have linear regression and support vector regression. Linear regression, what was introduced by Gauss 200 years ago, Gauss and Legendre. Support vector regression introduced by Vladimir Vapnik and Chevronentis in 1960s, more than 60 years ago. So all of these things have now been bundled into what we call machine learning, okay? So the building blocks of analytics, you need good informatics infrastructure, good hardware, good software, and most important, multidisciplinary teamwork. You have to bring people from many walks of life and get them to work together. And the tasks in an integrated analytics platform, data management, data laundering, assembling the data and getting a well-curated data set. I can tell you from our experience, and many people have shared this story, almost 70 to 80% of the effort in any analytics project is just here in step one. It is a painful part, but unless you have good data, it's really not even worthwhile proceeding ahead. Once you have good data, you can do data visualization, you can do exploratory analysis and so on, and feature engineering, decide which variables are important, which are unimportant, and so on. And then model and deploy, okay? All right, the other important graph to point out, this is mainly the work of Hinton and colleagues at the University of Toronto. They have been working on this image net large-scale visualization challenge, and this is the error rate. And look here, the error rate in 2010 was almost 30% and was steadily declining with the use of these multi-layered neural networks until in 2015, for the first time, it went below 5%. And that's even below what humans would do. If you had the same challenge for humans, you would perhaps incur an error rate of as much as 5%. So this was the big milestone which propagated the use of deep learning methods, and the start of the companies such as DeepMind and so on. All right. An important thing in working with data is how do you choose to represent your data. So representation learning is important. The performance of a simple machine learning algorithm depends heavily on the data and how you choose to represent data. People use terms such informative representation. You have to think carefully on how to represent data. Once you do that, you can then do feature extraction and decide which features are important and which are unimportant and so on. All right? All right, so I'm going to give you an example. Look at a bivariate system, such as the following: x1 and x2. If this bivariate system, when you plot it, appears in three very distinct clusters, you can easily separate them with linear lines, and that's how you want to represent your data. You want to try and represent the data which allows you to do easy clustering and classification. But on the other hand, if I give you this example, can you easily linearly sort out the green triangles from the blue dots? We can't do linear lines here. We can't do that. So the question is, how should we represent this data? So here is an example. Typically, we're trained to think in the Cartesian coordinate system or the Euclidean basis space, plot data like this. Instead of doing this, you can also transform this data, represent this data in polar coordinates. Have this as your center, measure the distance of each point by the radius and also the angle of each point. So each point will have a unique radius and an angle associated with it. And now, of course, in the polar coordinate, where this is theta, the angle, this is the radius, you can easily separate this. Okay? So now we can linearly. So this is just an example, and there are many examples, simple examples. You can do simple log transformation of your data, or represent data rather than impulse responses or as Gaussian kernels and so on. Okay? All right. Let's talk a little bit about these applications now. And so the first application that I want to talk about is the water application. Why should you care about water? The water food energy nexus is critical to sustainable development, because the demands for all three are driven by population increases, by urbanization, changing diets, economic growth, global warming, and so on. Food and agriculture, it turns out, are the largest consumers of water. 70% of the world's fresh water from lakes, rivers, and aquifers is used for agriculture. All right, 70%. Only 10% is used for domestic use, 20% for industrial use. All right. So we need to be mindful as water resources are becoming scarcer and scarcer and scarcer. All right. So here is an aerial image of the circular fields characteristic of the center pivot irrigation system. This is the pivot, a pipeline that runs on wheels as shown here. It's sucking up water from the center, from an aquifer, and this field, the diameter of this circular field could be more than 1 kilometer, easily 2 kilometers. So the whole center pivot rotates very, very slowly, okay? And you can draw different crops here. And the reason why irrigation is important because it is twice as productive as natural farming. So, and to supply food in a growing world population, we need to irrigate. The states of Nebraska, and just give you an example, the states of Nebraska, Kansas, Wyoming in the US, and Texas have such irrigated fields of over hundreds of square miles, and they're watered by the Ogallala Aquifer, a deep underground source of water that is now being depleted at record rates. And it's not the only example. So here is another satellite image of the circular fields. This is high up, and those are those fields, and each one of these fields could be easily 1 kilometer in diameter. So look at how intensive the agriculture field is. Okay. The Ogallala aquifer continues to deplete at record rates. From wheat and cows to corn and cotton, the regional economy depends almost exclusively on agriculture irrigated by the aquifer, by the Ogallala groundwater. So, in addition to water table depletion rates, there is significant nutrient loading in the wastewater. All the herbicides and pesticides that are sprayed, they go into the groundwater, contaminated the groundwater. Okay? And on the average, so I said 70% of the world's fresh water is used in agriculture. So agriculture is farming like this, but it is also dairy farming and meat in the meat industry. So just be aware, on average, it is estimated that it takes about 1,000 to 2,000 liters of water to produce 1 liter of milk. The water footprint for meat production is even more. It takes about, on the average, 15,000 liters of water to produce 1 kilogram of beef. So there is a lot of water, and so the water that's used includes water for the cows drinking, the feed irrigation, cleaning, and other aspects of dairy farming, for example. And so how do we solve this problem? And I just want to highlight this. It's not just in the US. Water below the surface can hide from the naked eye. There's no way we can see below the surface. But the GRACE satellite system from NASA consists of 2 satellites. These twin satellites can sense tiny changes in the Earth's gravitational field and the associated mass distribution, including water masses stored below the Earth's surface. And so they're able to sense changes in the water resources. And here is what this says. Rodell at GRACE and his colleagues did their case study. The team analyzed 6 years of monthly GRACE gravity data for northern India to produce a time series of water storage changes beneath the region's land surface. And they found that groundwater levels have been declining by an average of 1 meter every 3 years. So the water table is going down. Okay? And it's true also here in California as well. Look at the word land subsidence, sinking ground. And here you can see the sinking. So extensive pumping of groundwater from the San Joaquin Valley has caused widespread land subsidence. The newest area of concern is 1,200 square miles centered in the town of El Nido, etc., etc. And the ground is sinking roughly 1 foot per year. So what do we do? Well, so here is where these ideas of machine learning, sensing, and these would come in. You have a farmer's field. If we can measure the moisture content in the ground, if we can measure the nutrient content in the soil and the needs of the crop that you're planting, you could be planting millet or wheat or rice and barley and so on. If you could do that, if you could measure those things with the right sensing instruments. Now look at the challenges. The fields are huge. Where would you even put these moisture sensors, wireless moisture sensors? As the plants mature, the roots go deeper and deeper, and you need to sense the moisture deeper and deeper and so on. So many of the techniques, such as Kalman filtering, they come in handy, but you need good models, good agrohydrological models of these systems. So once you have a good mathematical model, plus some measurements, you can do state and parameter estimation. These are large-scale agrohydrological models, distributed parameter systems, so you have to really do a lot of grid work on them. You can feed that information to a scheduling and control algorithm. You can also take into account weather forecasting. If it's going to rain tomorrow, plants are very resilient. They can withstand a few days of drought, of no water, so you don't need to water and so on. So you can, once you take all of this into account, you can take the irrigation prescription, feed that, and irrigate the field. But the challenges are numerous. Sensing is the key one. And the other important challenge, and again, this brings to mind, the most important parameter is the yield. How much did one farmer get this year for rice, at the rice paddy? And all you have is one number. The yield this year is so many tons or kilograms of rice. Just one number. You may have had the right recipe, you may have had the right amount of water throughout the 3-month cycle, you may have had the right nutrients and so on, and yet at the end of the day you get one number for that farmer's field. So imagine collecting a lot of data. So you have to really put a lot of farmers to use, a lot of people to work on getting the right amount of data, building a very large database, a well-curated database that will then allow you to really move forward. There are many challenges. So here are the things that you need: weather forecast data, satellite imagery data, and this is increasingly being done. You have to fly drones over the field, get images, and infer the nutrient content and the moisture content from the crops. You have to calibrate it for the particular crop and the time of the year when you're doing this. So a lot of challenges in doing all of this. You need to build good agrohydrological models, each for a specific crop type, and then build ensemble Kalman filters and so on. So I show you this graph. This is the center point irrigation system here. You're taking water from the center and going round and round. Here is the field. This type of representation becomes very useful when you're dealing with fields such as the following. And my colleague Jinfeng Liu has been working in a field in southern Alberta, and they've been assigned a specific portion in a large circular field, and they're developing tools to estimate the nutrient content and so on. So a lot of math and Kalman filtering, extended Kalman filters, particle filters and so on that going into this to estimate the soil moisture. And models to look at root water uptake by roots. There is also a lot of transpiration, evoked transpiration from the plant, and so on. All of these things have to be taken into account. They depend on the wind and the rain and the sun, etc. Okay. All right. Let's now look at one other different application, and this is a step towards digital or computational pathology. And this is the work that we did many years ago for looking at malaria. How do you detect and diagnose malaria? Okay. It is typically done by looking at blood, stained blood smeared slides. And the microbiologists look at it through a microscope and look for parasites, such as the following. It's hard to see this with the light. You can see some parasites here. So the task of detecting the malaria, but it could be for other diseases. Tuberculosis is one, cystitis and so on. There are many different diseases that get diagnosed by looking at smeared slides of body fluids. So the task here is identification, detection. Are there parasites? One, enumeration, counting the number of red blood cells that have parasites, and speciation, which specific type of parasite is there. So you can then say, okay, this is the drug that will work. So in doing this, we were able to also get a size distribution of the red blood cells. And then if you have that, you can build a histogram. This histogram will give you a lot of information. If you have red blood cells that are torn and fragmented, you will get a very wide distribution, which again indicates the type of disease that one may be going through and so on. So there's a lot of things that can be done. And once you detect, you want to count the number of parasites. So we had developed a probabilistic k-means clustering algorithm that allowed us to count the number of parasites. And we compared this with some manually counted numbers, and it was quite accurate. So all of these techniques, this was done before deep learning methods arrived. Deep learning now, because it is highly amenable to working with images, can indeed help you. So this is the purpose in this slide here. And this is the challenge, and these are the type of projects that can really be done very well here. But not in the West because of the availability of a lot of information and resources here. So there is significant growing scope for computational or digital pathology. This field involves image analysis, machine learning algorithms to assist pathologists in the interpretation of slides and also checking on the diagnostic accuracy. The main challenge is to collect enough data, collection of sample slides for training and testing, collecting a well-curated set of slides for each and every disease, and making sure that the balance is right, normals, abnormals, and so on. So that's the big challenge. And so the more I think about this, data, pathological data, biological, medical data is going to be a priceless resource. People are already looking to try and bank this data, and they are going to sell this data. So you can do this. These are difficult tasks, but they can be done here quite easily. All right. Last application, I want to talk a little bit about battery technology. Very quick overview. Batteries have transformed our lifestyles in the 20th century. And of course, because of electric vehicles and so on, they promise to do so even more in the 21st century. All right, the Sony's battery in the 70s, it was the lithium-ion batteries, and they are the primary batteries in mobile phones and so on. So as we look to reach net zero emissions from vehicles by 2050, batteries need to become cheaper, have higher energy density, safer, recyclable. They need to be safer, they have to be recyclable and be made of ethically sourced material. Mining is a very non-environmental operation. It displaces people, it creates a lot of havoc and so on. So you need, if you're talking of sustainability and ESG, you have to bring all of these ideas in, all right? All right, and what's driving the interest? The high cost of lithium. I show you here, just within, from roughly $15,000 per ton, to almost $75,000 per ton, okay? So, net zero greenhouse gas emissions by 2050. We have to replace fossil fuel powered cars and trucks with electric vehicles. It requires lots of batteries. And so we have to look for more mineable deposits of cobalt, copper, lithium, nickel, and other materials as well. All right. So I just want to, even mining is now changing because of AI and machine learning. This is Eroom's law of mining. This is Moore's law spelled backward. Why? Moore's law is the observation that the number of transistors in an integrated circuit doubles about every 2 years. And it's still true today. The opposite is true for mining. Eroom's law of mining, the number of ore deposits are declining. And in fact, it is harder and harder to discover more ore deposits. Okay, so the discovered dollar cost of capital investment has been declining by a factor of 8 over the last 30 years. What we need to do is treat mining and exploration as an information science problem, and let's see what happens if we do this. So you want to combine geoscience data. A lot of it is available publicly, but it is highly fragmented and dispersed. It's everywhere. So putting it all together is the big task. But it is being done now. So you collect all types of data, geophysical measurements, electromagnetic measurements. They fly helicopters with a lot of sensitive instruments to measure induction levels everywhere, magnetic fields, seismic waves, satellite imagery data, etc., etc. Infrared bands, spectral reflectance, and so on. So they do all of this. And here is the result. This appeared, I don't know, you can't see the date here. This is 2023 June. 2023 June. The title of the cover article was The Great AI Treasure Hunt. So geologists in northern Quebec in Canada were able to dig for ore deposits using all of these techniques. And guess what they found? They were able to figure out 10 specific areas to drill using all of these measurements, and the success rate was 8 out of 10. So really contradicting Eroom's law, given all of this. So mining, again, to summarize, mining has become an information science problem. But think about this now. The same can be done in many other areas. If we put our minds together, if we put all the data together, you can really do amazingly well. All right? So mineral exploration and extraction is becoming an information processing science. So of course you combine AI, machine learning with geoscience expertise, and then do the same thing for batteries. And it is being done. Understand the electrochemistry, the chemistry of the battery. You need to have the physics and the chemistry of the material. Use AI, machine learning to accelerate the search for newer materials for battery electrodes and electrolytes, and explore different configurations for even solid-state batteries. That's the next generation. People need to be looking. Most of the current batteries have liquid electrolyte. They're looking for solid-state battery design. All right. One other thing, widespread applications of AI. This one, the article says AI can see the forest and the trees. Satellite imagery data will allow you to look at the makeup of the forest. Which species of trees are hardwood, which are softwood, which are prone to fire risks, and so on. Last year in Canada, we had thousands and thousands of acres of forest destroyed because of forest fire. And this allows you to assess the risk tinder dry conditions and lightning strikes, and a lot of forests just burn completely to ground. So this allows you to investigate these possibilities. All right, just one last application. I just want to show you a very simple application to say that you don't need rocket science to try and make machine learning work. So here is an example. How do you build a simple digital twin device to monitor its performance? If you have an actual process, an actual device, and if you could have a digital twin, a good model of that process, we can compare the outcome of the real process with the predicted, look at the error, and if the error is generally on the average 0 and bounded between two very narrow paths, everything is fine. If the error becomes large, you raise an alarm, all right? So here is this example. I show you here real data from a large pump, a pump in a desalination plant. This is the pump flow rate, here is the pump head. This is in gallons per minute, a very large pump. Imagine 2,700 gallons per minute, and here is the pump head. We know that pump operate on a specific characteristic curve. So depending on the head required and the flow required, you can operate the pump at a specific revolution per minute. So the pump would lie on one of these lines. And it's easy to obtain a model of this. It's a simple quadratic curve, all right? You can fit a curve. So we fit this data. Here is the pump flow rate and the head. The green data is what I showed you, and here is the equation of the straight line, or of the red line here. So this becomes our model, simple least squares, all right? Simple least squares. And we put that as our digital twin. We feed in the Q, the flow rate, and we measure the actual head and compare it with the predicted head. Again, the data analysis is important. You look at the error. Flow sensors are very noisy, very noisy. You get a simple air bubble in a differential pressure cell, and it causes havoc. It becomes a very noisy measurement. So here is the noisy measurement. All you need to do, so this is when you look at data ingestion, you have data like this. To make sense out of data, you need to pre-process the data. You need to massage the data. We could have easily filtered the data, and here, if this was the threshold on the raw data, you would get many red alarms, many false alarms when everything is running normally here. Here is the true abnormality. So instead we design a filter, we filter this data, and now no false alarms, and you're able to catch the abnormality very, very quickly. Okay? All right, I had other examples, but I'm not going to go through this. Let me finish. Again, that second example was supposed to show that you can apply machine learning algorithms. In that case, it was a support vector classification tool which allowed us to detect the abnormality quite easily. So to summarize, data ingestion, preparation of your data, lot of bookkeeping, pre-processing of the data, filtering and so on, data laundering or cleansing. This is a very, very important preliminary step. And 60, 70, as much as 80% of the effort can go in this particular area. And then you incorporate domain knowledge to formulate the analytics problem and the information extraction problem, and deploy your solution. So the other important thing to say is that I looked at three very diverse types of applications, and you can look at the applications of AI in many, many different areas. So look broadly and in depth for successful applications of AI and machine learning. Lastly, successful applications of AI and machine learning require a multidisciplinary team effort. You need to know the physics and the chemistry, the material science, or the engineering issues. If you're a farmer or you need an agricultural scientist, those farming problems are at the confluence of soil physics, water transport phenomena, meteorological sciences, and so on. So you need a multidisciplinary team effort to make these things work. And just some food for thought. Where do we go from here? The genie is out of the bottle. AI, ChatGPT, and Bard and other platforms are already out there. You can't put them back. So everyone, not everyone, but most people now have at their fingertips superhuman resources. Not everything that you get on the web is correct. You have to be very careful and you use your critical judgment. But given that, the question is, what do we do in schools and universities? How do we look at the curriculum? And what do you teach and how? And so on. That's food for thought. So anyway, thank you again, and I'm happy to answer questions.
Thank you for your talk, sir. I'm a faculty member here. My name's Kapadia. So my question is where you left off. On the one hand, it seems like you're saying everything is becoming an information science. XYZ is becoming an information science. You gave us a series of case studies. But of course, you also recognize the value of domain knowledge and expertise and so on and so forth, multidisciplinarity and so on. So from a curricular standpoint, how do you then, are our curricula currently in places like IIT Bombay fit for purpose when you are rigidly locked into a particular branch and have to kind of go quite deeply into that branch, and you don't really get the opportunity to explore laterally outside your branch? In other words, what if multidisciplinarity and if geoscientists have to become information scientists and information scientists have to become geoscientists, how do we simultaneously develop expertise and breadth, and what kind of curricula is adequate to that challenge?
Very good question. And really what you pointed out, therein lies the challenge. How do you assemble these teams? What I can tell you is that a few universities in North America, University of Toronto, for example, they've set up a vector institute where they're bringing in people from different areas and get them to work together on specific problems. So somebody from chemical engineering, for example, is looking at exploring a new process, and they want something different as an absorption material. So he has the material science resources, and he's collaborating with somebody who knows machine learning and so on. So it is no one person is going, you're completely right, no one person is going to know everything that needs to be done. This discovery of helicin was done by a combination of biologists, machine learning, deep learning experts, and so on. They put everything together. So it was, again, a team effort. But it is a challenge, and it's not going to start off just right there. You have to assemble the team, and there has to be also significant direction from up here. at IIT Bombay, for example, if you want to be now a leading institute in this area, you have to now have the directive from the top, and somebody has to say, let's put the resources and let's assemble, let's start the groundwork by putting in experts from different areas. Let get them.
Just to follow up, doesn't that require some kind of bilingualism on the part of it's not good enough just to be a material scientist. I have to be that plus.
Absolutely, yeah. Yeah, it completely requires bilingualism, yes. So, but you know, most people here, for example, when you are in engineering, everybody does some kind of analytics anyway, right? So there is that trend. I mean, but no one person knows everything as deeply as as is required. The other thing is also you need to look at novel problems from industry, from many other sources, societal problems. I just say this, people are looking at AI to monitor the diversity, the eco diversity in a forest, or they're looking at this to understand how glaciers are depleting and so on. So, there's so many different areas. If you go to Microsoft's website, they have a AI for Good lab where they're looking at a wide variety of different types of applications.
Thank you, Dr. Shah, for a very broad canvas that you painted. Is there a way to assess information content, richness of data, particularly when you want to develop models? Are there measures to quantify that and help the modeler?
Yeah. So certainly we're aware of, if you want to do system identification, you need sufficient excitation in your input data so that you can obtain a model. It really depends. Here, what type of data would work? Really, it depends on the specific question you're asking. If you want to build a detailed model, you would need a lot of excitation or a very large information content in your data. For digital pathology, you need, reference slides which have been validated by the expert saying, yes, there is this in this parasite here, and there is nothing here, and so on. So you need to collect all of these samples, feed them get images, and then train a deep learning algorithm to do all of those. So no easy answers. So depending on different situation, you will have some measure of the information-rich content required. The other important thing is the data that you provide will also invariably bias the output. There have been cases where people were monitoring potholes in a road by looking at your cell phone data. And it turned out, in the very beginning, the potholes that they identified were always in a rich area where people had the smartphones and they were feeding that data. So, and that wasn't what they wanted. They wanted to know potholes to be repaired in other areas as well. So there are built-in biases in the data that you collect. And you also need to balance your data, meaning if you're looking for abnormality in fault detection and isolation, if you only have one abnormality and 1,000 normal points, that's not, you need to make sure you have a good balance of normal and abnormal data to train your algorithms and so on. So all of this points to the fact that this data ingestion term, or whatever term, this first term that I use, is very critical. And a lot of industry is now gearing toward this. I was telling Mani, Google's acquired Kaggle. This is a few years ago now. I thought it was recent. And you ask, well, what's there? Because there's only data. Because they are now saying this data is now becoming a priceless resource. Good data. Not any data, good data. So good data, not big data. High quality data is what you want to collect and bank.
Thank you, Professor Shah. I think in the interest of time, we'll wind up. If you have any other questions, you can discuss over tea. So I'll request Professor Goody, our Dean ACR, to give him a token of appreciation from IT Bombay side. Thank you, Professor Shah, for this wonderful lecture once again. And just quick thanks to several people who helped in organizing this lecture. PRO office staff, CDEEP staff, VMCC staff, guest house, chemical engineering department staff, Dean ACR staff, and several of our colleagues and students. Also thanks to the Rajesh and Nisha Raman chair professorship, which made Professor Sirisha's visit to IT Bombay possible, which facilitated this lecture. And finally, thanks to the audience for sitting through the lecture, even though it's a bit late in the evening. So high tea is outside. You can join the speaker for high tea. Okay, thank you.